thank you everybody for coming here. I'm Lamberto Basti. I work at JetBrains, and I'm in the package search team for the users of IntelliJ, the new dependency tool window for managing dependencies. Now, let's start with the talk. So I want to show you Kotlin's flow, coroutines flow. So the first thing is, what's a flow? So a flow, it's the Kotlin stake on reactive streaming, on reactive programming. So when you want to react to events. So most of you here probably already know Rx in some ways, probably Rx Java or Rx Kotlin. So the next question is, why use a flow? So for the ones who haven't yet used coroutines, you may find out very soon when using coroutines that a lot of things that you need to deal with, they are given for granted with coroutines because you don't have to deal with them. For example, stuff like back pressure or, I don't know, callbacks. Everything you write is imperative and easier, actually. So also, you will find out very soon that you need a lot less lines of code to write the same things that you write with, for example, Rx or other reactive streaming libraries. So I'd like to show you a little bit how to implement some operators that already exist in the Rex world, and how to do it with flows and coroutines. So the first operators I want to show you, it's called partition. So this operator actually, it's pretty simple. It's not even available in Rx Java because it's just literally a filter, but I want to show you how to implement like this operator in with coroutines flow. And as you can see with this image, you have an upstream that emits values, and you just given a function that returns a Boolean. You want to understand if you want to split it in two new downstreams, one for the elements that return true to the function, one for the element that returns false to the function. So let's see how to do it. So first of all, let's see how to use this operator. So we create a flow of numbers, right? For the ones who don't know this function, this is the builder function for flows. Well, maybe it's better to, how do you close this one? Yeah. So this function that we see here, it's used to generate a stream of elements, a cold stream of elements, where you are inside this, in this lambda, you have a flow collector context. And in here, you just have available this emit function, all right? And so we are here basically iterating 100 times and emitting that number from 0 to 99. So we want to create this operator, which is down here. We're going to check details in a moment. And we want to return two new flows, all right? And with the structure, with the Kotlin syntax of the open parentheses, with the even flows and the odd flow, based on if the numbers that arrived from the upstream is an odd number or an even number. And then we collect it asynchronously with a launch. Now, let's see a little bit how this works for the ones who doesn't know enough about coroutine. So with coroutines, you have something called structured concurrency, which means that you can just spawn a new coroutine. And just to be more clear, a coroutine is something similar to a thread, but more lightweight. So what happens is that you can just spawn a coroutine from nowhere. There needs to be a parent. And the parent is the coroutine scope. So since we are already inside a coroutine environment, because this is a suspend function, we can spawn a coroutine scope, and inside of it, we can create new children. So what we do here, we spawn a children by launching a coroutine somewhere else, and inside of it, we collect the even flow. And in the meantime, in the current coroutine, we collect the odd flow. Now, we can run this because we still need to implement it. So let's see how we create an actual operator. So first of all, an operator is not a class, it's just an extension function of a flow of the type you want. In this case, a generic, because we don't care. And for partition, we just need to pass to this flow the function that is going to actually do the filter against the elements. This function is, of course, a lambda, and it's a suspend lambda, because you want to allow the user of this function to do suspend calls, like asynchronous calls inside the filter. So, how do we write this? Surely we need to return flow, so let's go flow 1 equals, we use the same builder, all right? So, inside here, we want to filter the elements that comes from upstairs. So, how do we open the upstream flow? Well, we can do this at partition dot collect. All right? So what we're doing here is that inside this lambda, sorry, we have available two contexts. Inside this lambda, we have available two contexts. One is the flow collector itself that we just opened. Another one is the flow itself on which we are calling the function on. So we can distinguish which this we're using by explicitly saying this it will be the flow collector, and this at partition it's the receiver of the extension function. But the point is the compiler is smart enough to infer this by itself, so we don't really need to, unless there are like functions with the same name from different contexts, we don't really need to explicit to this. So this function is going to be invoked, actually this lambda, is going to be invoked every time the upstream emits an element. And so what do we do inside here? Well, if the filter against the element, that we can call it here actually, element, against the element returns true, we emit the element to the downstream flow. Which flow? This one. Now we want to do the same on the other side with another flow, all right? Well, we can just, copy paste here. And we have a second flow. That's pretty neat because it's literally the same thing, but this time we emit if it doesn't pass the filter. And here we just return flow 1 to flow 2. All right, this is just for the one who doesn't know, this is just an infix function that returns a pair of two elements, and it's just simple. And now we've implemented the operator. Now, let's see a moment again what happens exactly inside here to understand what's going on. So, we return a flow to someone else. Let's see it from an outsider perspective, all right? It's from who calls this function. Who calls this function passes us the upstream flow in the form of a receiver, and we return to the caller two flows. Now, those flows are, of course, cold stream, which means they're going to start being collected only when you call collect on them. So when you call collect, for example, on flow 1, this lambda gets executed, and you start collecting the upstream flow. And if you can see on the left, there is a symbol on IntelliJ or Android Studio that shows you, oh, this is a suspend call. You're not going to go further in the execution of here, like you're not going to go further, because you're going to stop here and collect all the elements from the upstream until the upstream is closed. And for each element of the upstream, we're going to execute this guy here. And this guy here is going to just emit the element if it passes the filter. And we're going to emit it in this flow 1 here. And the same goes for flow 2. And then we return the flows. And that's it. Now, unless I made some mistakes, I can run it. Command 4. Oh, there you go. All right, as we can see, we collected all the elements And we printed them in a asynchronous way because the even flow, it's collected in a different coroutine than the odd flow. And, well, it's up to the scheduler to decide who to invoke first. So, yeah, that's it. Now, this was a simple one. Of course, it could have been implemented in easier ways, just with a filter. But I wanted to show you some of that stuff. Let's go to something a little more complicated to implement, especially in RX. Let's go to the take until, right? Now, the take until operator actually takes the upstream and copies it downstream until an event happens. In this case, from this example, there is another flow that emits an element, whatever element it is, whatever type, and as soon as the element gets emitted, the downstream flow will be closed. Let's see how we can do this with coroutines, all right? No, wrong desktop. All right, let's see first how we use it. So we have two flows here. This one is the upstream flow, where you emit a string, then you wait for 1 second. Mind here, this is not thread.sleep. Never use thread.sleep with coroutines, like never. Use delay. As you can see, it shows you correctly here that this is a suspend function and you are supposed to wait here. So then you send word, then you delay another 2 seconds, and then you emit nope. Now, we have a stopping flow, which I'm not really interested at the moment. And what we do here is that we take the flow, this guy here, we take until 1.5 seconds, all right? And then we collect. Now, what is this seconds? Actually, this is just an extension value in the standard library that just returns your duration. What's the duration? Well, time, whatever that means, 1.5 seconds. And then we collect the element, we stop here collecting, and we print everything in the same line. And then we do the same with the stopping flow this time. This is, of course, an overload that we're going to implement. And in the stopping flow, we delay 1.5 seconds, and then we emit just unit, because we're not really interested in the type we are emitting. Let's go for the implementation, shall we? We have, of course, two versions, one with flows and one with durations. But this time, we're going to use, instead of flow builder, we're going to use a channel flow. Now, why are we going to use channel flow? If we go back to partition, or wherever we use flow, actually, we can see it here. It's even easier. If you go to the documentation, right, great. Collects the value emitted by upstream. This method is not thread safe. So not only this method is not thread safe, which means that if on multiple threads you emit stuff, crazy things going to happen. But there is a check at runtime. If, bear with me for a second, if the coroutine context is different from the one that has been spawned inside here, whatever that means, coroutine context, at runtime there's going to be an exception. Now, if we look at this image for a second, we see that we have two flows here. One, the upstream, and another flow that we receive, which means that someone else, like some other coroutine, needs to watch the upstream flow and pass it down, and another needs to watch the other flow, the stopping flow, all right? So we need two, let's say, actors that does different stuff. Now, with a channel flow, what happens here is that we can't, what we want to do here, let's see a little bit, is we like to launch a new coroutine that actually passes through the elements from the upstream to the downstream. And it just so happens that the channel flow returns us, gives us a new context that produces scope. This producer scope is a send channel and a coroutine scope. Now, a coroutine scope, we already saw it before, allows us to launch a coroutine, right? A thing that I cannot do inside just a flow, because this is not a coroutine scope. And yes, I could do this all right? But this is gonna create a new coroutine context, as I said before, and this emit here is gonna be very pissed off about that, because this means it knows that it's not gonna be, you're using concurrency, and things might go wrong. So just use a channel flow. But a channel flow does not have emit, right? So now here we don't need coroutine scope anymore because this is already a coroutine scope. But it does not have emit, it has send. So what we do here actually is not that we just send. We launch, then in a new coroutine we collect the receiver, and then we send as is the element that is coming from the upstream. But why send instead of emit? So this send is, for sure, the point is to be thread safe. But this send comes from a channel, all right? Because the channel flow, channel flow is exposes or produces scope of a send channel. What's a channel? So a channel is like, a pipe, some kind of primitive of synchronization in the coroutine words, where you can put stuff with the send function and you can receive stuff from the channel, and it's both send and receive, they are suspending function, which means that you will suspend if the channel is full, and you will suspend until there is something to receive. And this is very important because it's going to give us for free back pressure. And we're going to see how to implement it properly, a more complex back pressure policy, in the next operator. Now, what we want to do here now is we are already sending downstream the elements. What do we do now? We want to take the flow that has been passed to us as a signal, and we would like to wait for the first element. And look here, what do we have first? So this function here, actually, it's a suspend function, as you can see on the left. So it stays here and waits until the next element arrives. And actually, it returns it to us. Well, right? So of course, from the signature, we don't know what element is that. But do we even need it to save it? Actually not. We just need to wait for it. Now, here, we will actually like now to stop doing this, all right? But we don't have a reference to it, but it just so happens that this, launching a coroutines, return us a job. And the job has the cancel function. So that's it. So we create a coroutine that sends downstream the elements, we wait for the first element, and when the first element is received, we cancel the job that was coming from the upstream. Great. Now, let's do something very similar for the other implementation, where we actually have a duration this time. Of course, flow.first makes no sense, but we already saw delay. So we delay for the given duration. That's it. And then we cancel the job. Pretty easy. So let's run it. So we expect hello world twice, and it worked. So let's see again the code. We have a flow here that sends hello, waits 1 second, and then sends word, and then waits 2 seconds. That's the upstream flow. The stopping flow waits 1.5 seconds, so it should, it should land more or less during this delay, all right? And then it emits unit. Here, it just waits 1.5 seconds, and then it closes the flow. So in both cases, nope does not get printed out, and it works as expected. Now, funny thing now, let's see the RX implementation. It's going to be fun. So there are a lot of things here. If you have time, we can go into details to see some goodies that the coroutines team have already prepared for us for interoperation between RX and coroutines flows. But for the moment, we want to see take until. The take until, it's called take. There are two actually. Take uses time, and take until uses an observable. Let's go for the observable. So we land in this magnificent 14K lines class. We need to go, so we add in the assembly line this operator here, which is actually a class, with, I mean, what isn't in Java, a class. We have some implementation in the parent, but we have magical 134 lines compared to just for one of the two operators. While here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. But I mean, like, you know, I mean, 3, 4, 5 if we consider the closing of the parentheses. So, yeah. And, you know, someone needs to maintain that code. So, yeah. Now, let's go to something more complicated this time. Let's go for group by. So this function is actually pretty useful, and given the upstream flow, we pass a function to the operator, which is gonna create a key given the value. So what happens is that from the value, we generate a key, and then for each key, we're gonna emit a flow only once, and all the elements from the upstream that generate that key is going to will be emitted in the specific flow of that key. Now, it's harder to explain it, but it's actually way easier to see what's going on. So basically, for each key, we want to create a new flow. So we're going to create a flow of flows, all right? Or, well, in Rx, an observable of observables that emits observables. Let's see how to do that. So let's first use it. So let's create a range of numbers in a new fancy way. This time we need the coroutine scope. So inside here we have a coroutine scope, and we can launch stuff, all right? And we go from 0 to 100, which means 0.99 as a fancy way instead of using the repeat, and we transform it to a flow. This is one of the fancy functions available in the standard library of coroutines. We want to use the group by that we're going to implement in a moment down here, and we want to group it by the last number that we have. So in the last number of the, number, so the units basically. So for example, number 25, 35, 45, they're going to have the key 5. The number 37, 87 are going to have the key 7, and so on and so forth, from 0 until 99. So we expect 10 groups. Do we expect 10 groups? Yeah, we expect 10 groups of 10 elements each. I believe so. Yeah. Well, so what we do is we start collecting them. And the group by is going to return us a flow of group by key item. So thank God this is not Java. A class is one line. And we have the key of that flow and the flow of the values associated with that key. So we destructure it during the collection here. So we have the key and the flow. And then for each flow, we launch so that we can collect it asynchronously. Because this collect is not going to invoke the next so if the upstream flow emits 2 elements, but we haven't finished executing this guy here for the first one, we're not going to start executing another one concurrently, all right? So what we want to do here is that we don't want to block the elements that come from the upstream, all right? So we just start collecting them in another coroutine. So we launch, we take the flow we just received, and we're collecting by printing key, whatever key is, and the number that now we are collecting from the other flow. All right? So let's implement it. So as usual, this is just an extension function. We have the key selector, all right, that given the value returns us the key, all right? Just a reverse map, more or less. So first thing first, somehow we need to remember what we already created, like the flows that we already created. Because let's say that we received the number 35, we created the flow, and we sent it downstream with already the first element inside of it. We receive now the number 45. How do we get the flow that we already emitted and push another element in it? So we need to remember stuff. So let's create a map for sure, a mutable map that from the key, as a key, makes sense, we return a flow of values. But a flow can only be collected. And that's not okay. We want to have some kind of primitive that allows us to send and also receive. So, you know, a channel maybe, but not Neo, no, coroutines. And a channel allows us to both send and receive, which is amazing, which is actually what we need, because we not only want to send stuff somewhere, we also wanted to receive from it, to collect the stuff. How we convert a channel into flow, we're going to see it in a moment. But spoiler, it's easy. So what do we do now? Simply, we're going to return immediately just a flow. No fancy channel flow this time, and we already have a channel to synchronize stuff. Actually, multiple channels. We return a flow, right? The compiler already did its job. We already inferred the types from the signature of the function. And so what do we do here? The first thing that we do is, we start collecting the upstream as soon as the user starts collecting the downstream. Let's take the value, call it value, right? So first thing is, let's evaluate the key. The key is key selector, and we invoke it with the value, all right? We have the key. Now we want to check if the key is already in the map. So if it's the first time we're encountering this key or not. So is key in map equals, well, key in map. Easy. Now, what we want to do is that we need to retrieve the channel, but the channel might not be in the map. So, well, channel equals map dot, we need to either get it or put a new channel. And look here what we have. So given the magic of the compiler, we don't need to put any types because, I mean, it's already declared here. Why should we put it here again? We put a channel in it, right? This is both a send and a receive channel. See? Both. So now, what we do here is, well, we take the channel. We know that this channel is of the key that we just found. So for sure, we need to send stuff inside of here. So we send the value. All right? Now, point is, at some point, we need to send something downstream because we are sending stuff in the channel, but how do we allow someone else to collect the stuff on the channel? So if the key was not in the map, what do? Well, we emit what? Well, this is a flow or group item by, and just to remember, group item by is just this neat, simple data class here. So we group item by key channel. No. All right. But yeah, sorry, Chanel. So channel. Of course, the compiler now is unhappy because it's not the right perfume. I mean, flow. And how do we convert it to a flow? Well, you know, consume as a flow. So this guy here just going to create a flow that is going to consume all the items immediately as soon as they receive it from the channel and send it downstream, all right? There are receive as a flow and consume as a flow. So consumers are the flow. The difference is that receive allows multiple multiple coroutines concurrently to receive from the channel, and based on the policies of the channel, stuff happens. But while consume as a flow, only one coroutine can consume that channel. And if another coroutine consumes that channel, well, that's an exception. So, and if the key is not in the map, we send it. Did I forget something? No. Now, this is actually a pretty neat implementation, couple of lines of something very complex, but spoiler, it's not going to work. It's not going to work because there are problems here with back pressure, default policies of back pressure. Just bear with me for a second. What happens here is that we have this channel, all right? And we try to send a value in as soon as we create the channel. Let's say that it's the first time we create the channel. This is a suspend call, right? Send a specific element to this channel, suspending the caller while the buffer on this channel is full. Okay. What's the buffer of this guy? Create a channel with a specific buffer capacity. The default is, where is it? Capacity after a positive. If I'm not mistaken, channel is rendezvous. What's a rendezvous? Well, rendezvous means that unless there is someone to receive, you're going to suspend and to send. That's no bueno, because it means that we haven't yet sent to anybody a way to consume, to receive from the channel. So this is going to stop here forever, classic deadlock. So one naive way would be to just move it after sending it. But who's gonna say to us that for sure that the user is gonna the user of this function is gonna consume right away, collect right away the elements of this function? Possibly another coroutines. We don't have this. We are not sure of that. So it just so happens that there are different ways for coroutines, for channels to handle a buffer, which is the key for one of the key ways for handling back pressure. You have rendezvous, of course, that you can't receive unless there is someone to, you can't, send unless there is someone to receive already. Buffer capacity, which you set a number and so on, unlimited, and conflated. Conflated, it's particular, as you can see, like there is always space to put something, but if another one puts some stuff, it's going to be deleted. Now we're going to just use, for this time, something simple. This time we're going to use channel.unlimited, all right? But point is that maybe, just maybe, the user of these functions wants to handle the back pressure, you know? So with specific whatever. So you do back pressure, or well, buffer capacity, and this is just happened to be an integer, and by default it's channel dot unlimited. All right, yes, and here we'll just put buffer capacity. All right, now we're sure that by default it's not gonna go in some kind of starvation or a deadlock or whatever, but the user might always F things up, so yeah. And this is gonna work, but let's look at the image again here. When the upstream flow closes, we'd like to close also the downstream and the generated flows as well. We're not handling any of this at the moment. So what we can do is that, well, actually, when the upstream closes, this stops collecting as well, and the flow closes. But before doing that, we would like to take the map the values, and for each, dot close. No. Yes. Now, when we finish collecting stuff here, before closing the upstream, closing the downstream flow, we will close also the generated flows. But what if during the key selection function passed by the user, there is an exception? What if while emitting this guy here, or here, the coroutine scopes get closed? So it happens, so just for the ones who doesn't know, the point of coroutines to have a structured concurrency is that the parents can be cancelled. And when it gets cancelled, all the children stops at the next suspension point. All right? How do they stop? By emitting a cancellation exception. All right? So if we cancel here, we go back here, the guy, it's a suspend function, is going to emit cancellation exception, and it's going to stop. And this line here, bye-bye forever. So what we can do here, simply put, is to try. Okay. And then finally, all right. And then we let the exception go on in its own life, whatever. And that's it. Let's run it. All right. So just again, we group by the unit of the number, and then we print it asynchronously as soon as we receive a new flow. Unless I did something wrong, which I did. I have no idea what that is. Really zero idea. Yep. As you can see, it's printing it asynchronously. Every key the right way, key 2, so on and so forth, until the last numbers, which are unordered for by design. Let's see Rx. So this is going to be fun. So actually, as you can see here, there are extensions on Rx observable source, so that you can collect them in a coroutines fashion, so that you don't need to rewrite everything every time. This is the group by, the one from Rx, Java, and it returns you this group observable, which is basically observable, but it also has the key here, which it's nullable for whatever reason. And let's go into group by. So we land at line 9,000 something. We have this group by with a lot of things that we pass. Of course, there is the identity function, but we already did that. And we land again on 9.999K over 9,000 and observable group by. All right, we land this magnificent operator, which yet again hides some of the stuff in the parent. And yeah, you don't want to be the one that maintains that stuff. So yeah, it's a lot of stuff that's how many lines? Sorry, almost 400 compared to like 11, 12. No, sorry. Yeah, 20 maybe. No, yeah, something like that. So that's it. Actually, how much time do we have left, more or less? 0, finished? All right. Let's close it here. Thank you very much.